Why is the sky blue? It's a question every single one of us asks as a kid. But the real answer? It's way more incredible than you might think. It's a story that doesn't just explain our own world, but actually takes us on a tour across the entire solar system, showing us skies you probably couldn't even imagine.
Okay, so let's just dive right in with a really fascinating puzzle. Our next door neighbor, Mars, has a sky that is the complete and total opposite of ours. We get these beautiful blue days and fiery red sunsets. Mars, it gets reddish, kind of butterscotch colored days and these strange, eerie blue sunsets. So, that's the big mystery we're going to solve today. How can two planets so close to each other be such perfect opposites? Well, the key to unlocking the secret of a blue Martian sunset is to first really understand the magic that's happening right over our own heads every single day. So, how does our blue sky even happen? Well, it really all comes down to just two key ingredients: pure white sunlight blasting from the sun and our planet's amazing atmosphere. The scientific hero of this whole story is a phenomenon called Rayleigh scattering. A guy named Lord Rayleigh figured it out way back in the 1870s. And the core idea is actually pretty simple, but it's incredibly powerful. When light hits really, really tiny particles, the color of that light matters a lot. It's all about size. So let's break down how this works. Picture this. First, sunlight, which has all the colors of the rainbow packed inside, comes streaming into our atmosphere. Second, that light starts bumping into the billions and billions of teeny tiny nitrogen and oxygen molecules that make up our air. And third, this is the magic part, because blue light travels in these short, choppy little waves, it gets bounced around and scattered in every direction by those molecules, basically painting the whole sky blue from our perspective. And just how much more does blue light scatter? Get this, it's not even a close competition. Because of its short wavelength, blue light is about 9 times more likely to be scattered by an air molecule than red light is. That incredible difference is the reason our sky is so intensely blue. Okay, so that totally explains the blue daytime sky. But you're probably wondering, if blue light gets scattered so easily, why do we get those amazing red and orange sunsets? Well, it's the exact same science, we're just looking at it from a different angle. Here's the key. At noon, the sun is pretty much directly overhead, so its light takes the shortest, most direct path through the atmosphere to reach you. But at sunset, the sun is way down on the horizon. That means its light has to travel through a much, much thicker slice of the atmosphere to get to your eyes. And that extra long journey means there's just more air, more molecules, for the light to fight through. By the time that sunlight finally gets to you, almost all of the shortwave blue and green light has been scattered away, off in other directions. So all that's left to travel in a straight line to your eyes are those beautiful long-wave reds and oranges. All right, so now that we're basically experts on Earth's sky, we have all the tools we need to solve the Martian paradox. Remember that whole opposite world thing we started with? It is time for the big reveal. See, on Mars, pretty much everything is different. The atmosphere is incredibly thin, like only 1% as thick as Earth's. So the gas molecules themselves don't do much scattering. No. On Mars, the real star of the show is the fine red dust that is always hanging in the air. These dust particles are bigger than our gas molecules, and that completely changes the rules of the game. This Martian dust is full of iron oxide, rust, and it's just the right size to do something different. Instead of scattering the short blue waves, it's much better at scattering the long red waves all around the sky. There's a different name for this, me scattering, and it's what gives the Martian sky that famous reddish butterscotch color. And this is where it gets really wild. When the sun starts to set on Mars, its light has to travel through that same dusty, thin air, and it leads to a total reversal of what we see here on Earth. So those exact same dust particles that make the day look red do something amazing at sunset. They scatter the red light away from your direct line of sight. But the blue light? The blue light gets scattered forward, almost directly along the sun's path toward you. And the result is this incredible, concentrated blue glow that forms a halo right around the setting sun, the perfect opposite of a sunset here on Earth. But hey, Earth and Mars are just the beginning. Once you get the hang of these principles, atmosphere and scattering, you can start to explore the skies all across our solar system. It's like a gallery of alien worlds. Let's take the Moon or Mercury, for example. They have basically no atmosphere. And if you have no particles, you get no scattering, no color. So the sky is always just a deep, silent, perfect black, even when the sun is shining right there. Now, Venus is the other extreme. Its atmosphere is about 90 times denser than ours. It is so thick and crushing that it scatters light like crazy, trapping the whole world in what looks like a permanent, hazy, deep orange sunrise. If you travel out to Saturn, you'd be looking up at a hazy, yellow sky. And that pale color, it comes from tiny ammonia crystals floating way up in its atmosphere, which happen to be really good at scattering yellow light. And finally, you've got the ice giants Uranus and Neptune. They get their absolutely gorgeous colors from methane gas. See, methane is fantastic at absorbing red light. So when sunlight hits their atmospheres, it basically eats the red, and only the blues and greens get scattered back out. That's what gives Uranus its soft cyan color and Neptune its stunning deep royal blue. So what's the big picture here? After this whole tour, from our familiar blue to the red days and blue nights of Mars to the yellow haze of Saturn, what does this all really mean? Well, the thing you should really take away from this is that the color of a planet's sky isn't just a pretty detail, it's a scientific fingerprint. Just by looking up, you can tell what a world's air is made of, how thick it is, and what kind of dust or crystals are floating around up there. And that really makes you wonder, doesn't it? If our own little solar system can create this much variety, what other impossible, unbelievable colors might be painting the skies of all those exoplanets out there, orbiting distant stars, just waiting for us to discover them?